Hello and welcome back to Calculus 3. We are going to discuss chain rules, plural, because there are many. So in Calc 1, you had one formula, one procedure, one idea, and you do that and you're done. For now, you are going to look at what type of the problem you have, how many independent variables, parameters, everything. And then you will maybe construct a tree. And once you have the tree, which is a tree diagram, then you will write the formula which you are to use to find the derivative. To refresh from Calc 1, so Calc 1 first, as usual. If you are to take derivative in respect to x of, let's say, e to the x squared plus 3, you would say that e to the x is the main kind of function, and then x squared plus 3 is composed with e to the x, so it's plugged into e to the x. So the derivative would be e to the x squared plus 3 and then times 2x, which is the derivative of the inner function, if you want to say. And that was it. Now, what we are going to have is, we are going to have a function w that might be a function of xyz, and then each one of these xyz's could be dependent on different parameters. So you can have a maybe parameter t only driving each one of these, like we had so far. Remember the vector valued function and so on, or just parameter t. But you could also have maybe s as well, or maybe even more. So this is going to create a different formula for every time when you add either a variable or a parameter. There's no one thing that you are going to memorize. You are going to learn a procedure of how to figure out the diagram, and then from there you will just write out a formula. So let's start with just two variables and a single parameter. That's the cheapest we can go in Calc 3. So two variables and one parameter. This means that my function z is a function of x and a y, and then x is some function of t, and y is some other function of t. So now you see that function gt is plugged for x and function h of t is plugged for y. So now you are plugging functions inside the function. That's the function composition. But because we have a two-dimensional domain, right, we're having two functions plug in instead of earlier just one. So now, if I am to look at the diagram for this, I will say that z is made of x and a y, and x and a y are both made just of parameter t. This is the simplest possible diagram that you can have. So now, what is the derivative? Sorry. Well, the notation will be a little bit tricky, but you'll get used to it. What is the derivative of z in respect to t? Well, this means that you are supposed to travel from z to each t down each branch that connects z to t anywhere, which is this branch and this branch. Now, actually, I'm going to do the other one blue. So now, if you look at this, observe that function z is composed of two functions x and y, which is where the partial derivative kicks in. So if you go down the red line, you have to take the partial derivative of z in respect to x and multiply that by the derivative of x in respect to t. So that is going down the red line, and we add to that the blue line, which means we start the partial derivative z in respect to y now, and then we have dy dt as the chain rule. Now, you might go immediately and ask, what the hell is going on? Why do we have partial derivatives and regular derivatives mixed in the same formula? Well, observe that anytime I use the partial derivative, and that will be more obvious as we go on through these exercises, anytime when you have the partial derivative in the formula, you will have this kind of a split. A single variable that is on top will be splitting or 2 or 3 or 4. And anytime when you have a regular quote-unquote derivative, you have a straight through going down a single assignment x to t, because that's technically only calc 1. Would you be wrong if you used partial derivatives everywhere? The answer is no. You can actually use partial derivatives everywhere, and we could actually, in mathematics, we could just use partial derivative notation throughout calc 1, 2, and 3 without ever having this good old d that you are used to. What you cannot do, though, is reverse it and have the regular good old d in place of the partial one. That you can do. Now, that's the formula. We look at the problem, see how many variables we have, and then we draw the tree, and from there we create the formula. Now, this f of xy is given, you can find, so when f of xy is given, you can find these two guys, and then from these two, you would find the other two, so you can obviously put everything together. So let's take a look at the spicier example. Say now, you have w as a function of x, y, and z, and say that x is a function of s and t, and y is some function s of t, and z is some function of s and t. How many branches are you going to have all the way at the bottom? 6. Very good. You already see it, and that's great. So the tree. We are starting with w on the top, and that one branches into 3, x, y, and z, which we see here. So the first branching is done at the main function level. So the w branches into x, y, and z. Now, from these secondary functions here, we see that each x, y, and z branches into 2 additional branches. So we are going to branch each one of these and give them st, st, st. Now you have 6 branches here because you go from w through x to s, from w through x to t. That's 2 branches already, and then another 2 and another 2. Or you can just see there are 6 values on the bottom. So now, if you are to find the derivative of w in respect to t, the first thing you say, whoa, those used to be the regular d's last time. Well, now you can't have the regular d because you have a partial from w to x and you have a partial from x to t or s. So partials everywhere, you can't have a regular d. Now observe. You see that we are looking derivative in respect to t. T only has 3 branches, not all 6, just 3 out of 6. So we have to follow only the branches which end with the variable that you want, in this case t. So I'm going to walk this branch, and this branch, and add them. So you are just following the tree. We have a split, which means partial w, partial x, another split, partial x, partial t, plus a split into a y, so partial w, partial y, a split s and t again, partial y, partial t, plus a split, so partial w, partial z, another split, partial z, partial t. You have to create this formula every time, depending on the problem. I can give you 2 variables, x and y, and 6 parameters. That's going to have 12 branches, right? It can be any situation. We have to have in engineering this kind of this possibility to run as many parameters. Think about how many parameters would impact a certain thing which impacts something else. I'll give you the most mundane example. Is it going to rain? Do I bring umbrella or not? Right? Depends on the weather. The weather depends on the temperature, the pressure, right? So you have a whole bunch of parameters that will contribute to the weather, that will contribute to whether I bring the umbrella or not. Take the car, how many different parameters you have in order to have a unit that actually works and is marketable. A plane or whatever else you are creating. So we have to have the freedom to have as many variables, as many parameters to drive our end product at the top. So no formula here. Your job is to learn how to create the tree properly and then just follow down the branches to get the derivative. Now, we also have partial w, partial s, which would be, cut and paste this previous line and replace all t's with s's, because all of the branches are the same, except now you end with s rather than t. So partial w, partial x, partial x, partial s, plus partial w, partial y, partial s, plus partial w, partial z, partial s. And these are the derivatives. Just follow the branch. Yes?
So When you wrote the first one, the two variable single parameter, some of them you wrote as d's, some of them you wrote as deltas. Is there a reason for that, or are they pretty much the same thing all across?
As I said, every time when you have branching,
Right.
you have these guys.
Okay.
Every time you go straight through, you have these guys. The last example we did only has branching. It doesn't have a straight throughs anywhere. All right? So let's have a ridiculous tree that we're not even going to try to write functions for, just to actually write the formula looking at the tree. So let's see. What is a partial W partial R in this case? Done. Walk away. Very good. There is only one branch that leads from W to R. I want only one branch, right? I only want branches that go from W to R because that's what I'm looking for. Partial W, partial R. Let's see. How about partial W, partial S? So who's going to tell me what to write? Yes. Beautiful. There you go. That's what it is. And obviously, if I'm to ask partial W, partial T, it will have all three branches, right? Because T shows up in all three. Ah? Nope. Sorry for disappointment. Alex.
Yeah.
And you know why, right?
Yeah, because straight through as opposed to
Branching everywhere. Yep, great. All right, it's time to work on a problem. Now they do split this into multiple sections in the lecture and so on. You guys have a straight shot for all of these. So let's see. I don't remember what was the date. What was the date?
He doesn't enforce these things, right? As long as it's in by the final. No, we're definitely not.
So well kept.
It's gonna be kept all over Monday. Monday's probably reasonable.
Lab is due Monday? I don't know. Is it?
Monday.
How about Wednesday?
Wait a minute. Hey. What are you doing? Squared or S squared for X?
S. Like position. S, like position, right? There's an S in there. Yeah.
would not have done this.
You need to go one step. You just writing it out. So that you feel better about it. Okay, so neat.
That's pretty small.
So do we all have this line?
Yeah.
Partial z, partial x, partial, so you're taking the derivative in respect to x. So that's going to be cosine of this times 2, right, from the chain rule. And then times the partial x is 2s. This is a constant that it dies, right? So that's that. Plus partial z, partial y is cosine of 2x plus y, the derivative of that is 1. Times again 2s, partial y, partial s is 2s again. Now, are you done? Yeah, hell no, right? We have to plug in x and a y in terms of s and t and simplify because we have to have in respect to s, which is the parameter. The problem is asking you to find the derivative in respect to s. The hell are you going to have these x's and y's floating around, right? So now you have your x, you have your y, you plug those in, and you simplify everything, and now it's going to be in terms of s and t. It's okay to have t around, it's not okay to have x and a y. For s cosine 2x, that's going to be 2s squared minus 2t squared plus s squared plus t squared plus 2s cosine 2s squared minus 2t squared plus s squared plus t squared. Damn. Which is equal to 4s cosine 3s squared minus t squared plus 2s cosine of, again, 3s squared minus t squared. What can we factor? Oh, these are the same, so just 6 of these, right? Is this good?
Yeah.
But there's nothing above.
Yeah. That's so cool. So.
All right, so this over here is your 2x. This over here is your plus 1y. And then you go from there.
What would happen if you plugged in?
It's easy to solve. I know you see it already.
Still coming down?
Two problems on chain rule on the exam. One is some simple calculation like this, and one is probably some really crazy tree just to create a formula without calculation. So one is for kind of theoretical, do you know how to create a tree, and the other one would be something that is not going to take you 30 pages to grind through as you solve this.
This would be more like the first or second problem.
This is the calculation problem.
Or like the second problem.
What do you mean second problem?
Like the ones you mentioned, so it's going to be 2 types. So would this be more like theoretical? Or more like
This one is calculation. It's not a theoretical because you have a derivative at the end. It's you did the problem. The theoretical part is creating the tree. So this one is I give some crazy tree and I say write the formula. And your textbook has beautiful examples for these things to practice. Then that was, we still have to find the t, z of t. All right, so let's see. Now the next part is to find partial of z in respect to t. Same problem. Which is going to have the same formula as this one, except you're going to have t's. So partial z, partial x, partial t, plus partial z, partial y, partial t. The cool thing about this is you get to recycle partial derivatives and just add the stuff that involves t. So you recycle the first partial derivatives, which are the 2 cosine 2x plus y. And then we multiply that by the partial x partial t, which was, if I remember very well, negative 2t. And then plus, we recycle this one as cosine 2x plus y. And then again, second one was positive, right? Yeah, so positive 2t. So we can actually combine them first. So I have negative 4 and then positive 2, so all together is negative 2. Cosine of 2x plus y. And we can plug in, so that's going to be 2t squared minus 2s squared plus t squared plus s squared for total of negative 2 cosine 3t squared minus s squared. We all good? Need more examples? Yeah, it's clearly there. Look.
Oh. Sorry, my glasses were a little fogged up. You know, they really are. My eyes fogged up. I have fogged up. Hey.
What happened?
I was terrified of how long came off when you said that.
S minus t or t minus s? S minus t? I have this switched. So this is supposed to be S and T and S and T and S and T. Better? Thank you.
Wait,
Yep.
what about for the first one?
The first one is correct.
First one is T and then S.
No, it's S and T.
Wait, but stream, all right.
The stream line.
So I did have it right.
David, never doubt yourself. The stream will all adjust the way you do.
You guys are genius.
Questions, concerns on chain rule? All right, then that's done. Now let's see what else we're going to do. Let me say bye.